Hi everyone, welcome to the lecture for Lab 7, which is all about fronts and weather systems. So the objectives for today's lab are we're going to identify the source region for US air masses. And so we'll talk in the first part about what air masses are, but basically we're looking at these kind of giant blobs of air that originate in certain places and affect the weather in the US. We're going to identify the humidity and the temperature of those air masses. And then we're going to identify the location of warm and cold fronts in cyclones. And this is going to be a whole kind of area on weather forecasting. We're going to determine current weather conditions based upon a frontal map, and we're going to forecast those conditions. We're going to calculate time delay for thunder. So that idea of when you hear a clap of thunder, you see the lightning, hear a clap of thunder, you can calculate how far away the storm is. And lastly, we're going to identify cloud types. So this lab is much longer than the last lab. It's not too terrible, but it is longer than the last one. We were kind of lucky to start with our distance learning on a short lab week. So part one is all about air masses. And again, just a quick reminder, if you're watching this lecture, you're going to want to have already opened the lab. You're going to want to open either the Google Slides or the PowerPoint file on Canvas. So air masses are basically these gigantic bodies of air, and they differ based upon where they are formed. They have different characteristics, whether or not they were formed over land or water, and at what latitude they were formed. So if they're formed farther away from the equator, they're going to be colder, as opposed to if they formed near the equator, they're going to be warmer. And they expand and contract, and they interact along their boundaries. So this is an air mass map of the United States, and this is in your lab. And so I'm going to switch over to the lab, and I'll explain what it is that you have to do for that lab, but we'll start on page 1. So here is the things that I just went over, and we're talking about these air masses. So this part we're going to fill in together. So air masses either form over continental or land locations, or they form over marine or ocean conditions. Tropical air masses form near the equator or in the tropics. Polar ones form farther away from the equator. So we're just going to simply here put in the characteristics of an air mass that forms over a continental location. Because the air mass is forming over the continental location, there's not a lot of moisture to pick up there because we're over land. So this air mass is going to be dry. Conversely, if we form over a marine location, this air mass is going to be humid or wet. If we form over a tropical location closer to the equator, our air mass is going to be warm. And if we form over a polar location, our air mass is going to be cold. So you should fill those guys in right now. And then on the next page, this table is kind of putting all of that information together. So we'll do the first one together. An air mass will have 2 letters. So a CP air mass would be a continental polar air mass. So we would put in here continental polar. And then we want to know, excuse me, if this air mass is warm or cold and whether or not it's dry or humid. So a continental polar air mass would be dry and cold. So now you're going to finish the rest of this table looking at these different air mass characteristics and their name. The next thing that you're going to do is move on to figure A, which is down here, and you're going to label what these air masses are using that 2-letter system. So The circle is where it is formed, and the arrow is where it is moving to, right? So these six air masses converge over the United States. So again, where the circle is, that's where you're looking for its classification. Where the arrow is, that's where it's moving to. And so if we go back up, and then you're going to answer a question kind of based upon what you did. So that is all of part 1, which is about those air masses. It's pretty straightforward and pretty simple. I'm going to go back to my lecture now. The second part is all about frontal systems. And frontal systems are basically boundaries between air masses of different temperatures. They are most common in the mid-latitude, so right over the United States. There are 4 different types of fronts, and this is based upon how those air masses are moving. But the important thing to remember is that warm air is always getting pushed up over cold air, causing clouds and often rain. But it can look different based upon what's happening. So we're going to go through the different types of fronts. And these types of fronts are also in your lab. So the first one is a cold air front, where you have a cold air mass over here and a warm air mass over here. And the cold air mass is overtaking the warm air mass. It's pushing into it. Now, cold and warm are relative terms. This could be a 65-degree air mass, and this could be a 75-degree air mass. It doesn't have to be freezing and hot, right? This could be a 40-degree air mass, and this could be a 25-degree air mass. Those are relative terms to one another. When a cold air mass overtakes a warm air mass, that air right here gets pushed up very quickly, and the pressure drops very quickly. And you get these cumulus clouds. We'll talk a little bit about clouds later. Often thunderstorms, heavy rain. The temperature will drop, but that cold is relative. So again, you can have a cold front come through in the middle of the summer. It's going to get cooler, but it's not necessarily going to get cold outside. So the front is the boundary between the 2 air masses, not the 2 air masses, it's the boundary between the 2 air masses. And on a map, a cold front is represented by triangles, blue triangles, that are pointing in the direction that the cold air mass is moving. Next, we have a warm front. And so this is where you have a warm air mass overtaking a cold air mass. So it's represented on a frontal map using these red half circles that are pointing in the direction that the warm air is moving. And rather than the air being shot up quickly, the air ramps up slowly over that cool air and the pressure drops slowly. And you get stratus clouds, which are these layered clouds. They're just past the front. So in the cold front, the rain was right here. In the warm front, the rain, because it takes time for that stuff to cool and get to a high enough altitude for you to get those clouds form. So we're going to have rain past the warm front. And at high altitude, we're going to get cirrus clouds. So cirrus clouds are basically the same kind of type of cloud where the air is moving horizontally, except it's at a much higher altitude. So it's going to be cooler over here. You're going to get moderate precipitation right here, warm and dry behind the front. Temperature rises, but again, that warm is relative, right? So this could be a 40-degree air mass. This could be a 30-degree air mass, right? As it's come through, it still feels pretty chilly, but it's going to warm up some. Stationary fronts are where you have 2 air masses of different temperatures, but neither one is overtaking the other one. So it is represented by these interlocking symbols. So in this one right here, the warm air is over here and the cold air is over here, and they're just kind of butted up alongside each other. You get some light rain, if any. You do still get some air that's rising over that cold air right along this frontal boundary. It's not some type of big dramatic rain event. This is often the start of a mid-latitude cyclone. Um, and mid-latitude cyclones, we have lots of them in the United States. So these storms that kind of originate over the Pacific Northwest and then move across the United States. And I'm going to show you what that looks like after I show you the last front. So the next front is an occluded front, where basically you have two fronts involved. You have a cold front here, remember the fronts are the boundaries, and a warm front here. This cold front is moving faster than this warm front. So this cold front is going to catch up to this warm front. And when it does, it is going to, like a bulldozer, just lift that warm air right off the ground. So you'll wind up with a blob of cold air on the bottom and a blob of warm air on the top. So you start with two separate fronts, a cold front and a warm front. You wind up at the end, here you have three air masses, cold air mass, warm air mass, cold air mass, but these two cold air masses will connect, so you'll wind up with one cold air mass at the bottom, one cold air mass up above, so that cold air just gets wrapped around that warm air. That warm air gets completely lifted up off the ground. And this symbol is purple on the map, so because blue and red make purple, and you get both symbol types, the triangle and the half circle. So let me go over to the lab for a second so I can show you. There we go. So in your lab, you have descriptions of these fronts, which I put them in there for you so you could use them while you're doing the lab. But you also have the slide on the mid-latitude cyclone. And I have this in here, not so much that you have to do anything with the mid-latitude cyclone, but I just wanted you to understand how weather moves across the United States. So we start with this stationary front over here, which I talked about a minute ago, and then you kind of get the center of low pressure, and then you get this defined cold front and defined warm front. And this whole thing, right, is spinning as it moves across the United States. So this cold front is being pushed up, the warm front is, and sometimes these guys will occlude right here. So in this lab section, the first thing that you're going to do is you're going to fill this out. You're going to drag these purple letters, purple text, kind of where they go on this transect of a front. And you're going to notice, hopefully, that it looks an awful lot like this, right? So you're going to fill this out, and you're just going to drag these guys kind of where they need to be in as close of approximation as you can get on this figure here. And then you're also going to have to tell me the overall direction of the air here, which way it's moving. And in order to do that, you're going to have to rotate this and spin it around. The next thing you're going to do is on figure B, which is a frontal map, you're going to label by dragging and dropping the warm air section, the cold air section, the area of heavy rain and thunder, which is in purple, the area of light rain showers, and the area of light rain around the low pressure cell. So when we have low pressure, we generally have wet weather. And so if we go to that figure, these guys that are on the left, you can drag them around and move them approximately where they need to be on this figure. So light rain, you have to rotate them a little bit to get them in the right spot. Potentially light rain, heavy rain, cold air mass, warm air mass, and then rain around the low pressure system. And then we're going to move on to actual forecasting, right? So now that we've talked about how kind of weather moves across and what types of weather you get at different fronts, you're going to go back to this map here, And there are some cities labeled in, and you might have to zoom in. This is kind of the best map that I can find to use here. Usually we're kind of drawing this on a figure in class. But you can see some cities: Denver, Topeka, Jackson, Little Rock, Frankfurt, Augusta, Harrisburg, Pennsylvania, Albany, New York, and Tampa, Atlanta. So there's quite a few on there. And what you're going to do is this first part A, it's asking you to identify which city, don't tell me a state, a city, has these current weather conditions, cold temperatures and clear skies. It's possible there's more than one answer. You don't have to give me both answers. And then we are going to go through and fill out this table, and you are going to tell me at these different cities what the current temperature is. So in all of these boxes, you should write warm or cold. That's it. What the current precipitation is, none, heavy, or gentle. The forecast temperature, I want to know, is it increasing, decreasing, or no change? And then the forecast precipitation, I want to know if it's going to be heavy, gentle, decreasing, or there's going to be no change. So again, you're going to go back to that map. We talked about how these fronts move across the United States, and they're spinning and being pushed across the United States. So based upon that information, you're going to do some weather forecasting using this map. And again, you're going to have already moved these weather systems, and you're going to have to understand how the sky is moving across the United States. Let's go back to my lecture so that's the weather forecasting. Part 4 is very straightforward. It's all about thunder and lightning. And so we get thunder because we get these positive and negative ions that get separated inside of a cloud, and then they snap back together and they discharge it, electricity. And when they discharge that electricity, we see lightning and hear thunder. Sometimes we don't get to see the lightning, but that's what the thunder is. And we know a couple of things. We know that sound travels at 335 meters per second, or 0.208 miles per second. And we know how to figure out a couple of simple formulas. Distance divided by rate equals time, or rate, again, this is the rate, times the time equals the distance. So light, we don't calculate the speed of light because it's so fast, it doesn't really make a difference for here. But on your lab, what you're going to do, let me go back to my lab and go to, right, so here is that same formula I gave you here. And basically, you're going to want to use these very simple formulas to answer these couple of questions. So if you see a flash of lightning, how many seconds should pass before you hear the thunder, right? So what are the things that we know here? We know the distance is 3 miles, and we also know the rate. So because we know the distance and the rate, this is the equation we should use. We want to figure out the time. So we would take the distance, 3, and we would divide it by 0.208, which is this guy right here. Right? That's my distance divided by my rate. Make sure if this distance is in miles, you are using miles. If this distance is in kilometers, you're using the kilometer one. So make sure you use the right one. And so we would divide that, which I'm going to do on my calculator, which you can't see, but I'm doing it right now. 3 divided by 0.208 equals 14.42 approximately. That's how many seconds, right? It asks you the seconds. In the next one, you have a different formula. It's giving you the time, right? It wants to know how far away you are. So now we are not going to use this formula. right here, we're going to use this formula. We're going to do the rate times the time equals the distance. And again, pay attention to what it's asking for. So here it's asking for the miles. So the rate for miles is 0.208, right? And then let me go back to that little thing. There we go, right? So we are going to take the rate, multiply it by the time, and we're going to get the distance. So the rate, we're going to multiply it by the time, and 0.208 times 3 equals 0.624. So that storm, if it took 3 seconds between the flash of lightning and the thunder, is 0.624 miles away. Again, pay attention to the units that it's asking your answers for in. This is pretty simple math here, so I would like you to show it to me in your square here. Don't just type the answer. I would like to see the little equation that you used to do it. And then it's going to ask you kind of a general question based upon the things that you did. Last part is all about clouds, which is more or less just kind of filling in a table based upon some information. And then you have this kind of very nice illustration of where clouds are and what type of weather you get. But they are, as this says, visible expressions of condensation and indicate current weather conditions. So you get different types of clouds based upon their shape. It tells you which way the air is moving and what type of potential weather effects you're going to get. Clouds are classified by two characteristics, their altitude and their shape. So cirrus, alto, and stratus, that means high, middle, or low. And it's these elevations here, 20,000, 6,500 to 20,000, or below 6,500. This is the area of elevation that you're looking for here. And then shape, stratus also means horizontal and sheet-like. Cumulus clouds are round and puffy, and generally low, but cumulus clouds rise up, so they're kind of at multiple elevations, but the bottom of them are low. And then nimbus means any cloud that is precipitating. So you can have a cumulus cloud that is not raining, or you could have a cumulus cloud that is raining, and then it would be a cumulonimbus cloud. So on the next page, it says to classify the clouds in the table on the next page based upon the information above. And you can also look at figure C for an illustration of cloud types. We also have this nice cloud illustration to tell you kind of what it looks like. But again, cumulus clouds are rising air. So their bottoms are at a low elevation. So I filled that one in here for you that says low. These are your weather conditions right here that happens with each cloud. And so the first thing that you're going to do is put in the altitude. So if it is high, middle, or low, and if you look for the word cirrus on this previous page, you can see cirrus is a high cloud. So you're going to put that high in here. And then you're going to look up that information on multiple clouds, all these different types, and fill in their shape, which their shape, again, that's listed right here, horizontal and sheet-like, round and puffy. Oops, sorry. And then you're going to answer a question based upon what type of clouds do we have today. If you're doing this for most of this week, if you are in Southern California, it's raining. So we definitely have clouds. And what does that indicate about our current and forecast weather conditions? So that is it for Lab 7. Again, you'll either submit this through Google Assignments or you'll save it as a PDF and submit it right on Canvas. Feel free to make an office hour appointment with me if you have some questions, and good luck.